Hi there, students. Welcome to Trigonometry Day 3. This is Mrs. Brunk. Today we're going to learn about angles in standard form, and we're also going to learn about a unit called the radian. And then finally we're going to look at how we can relate the trig ratios of the sine and cosine and tangent into triangles created in the coordinate plane. So our first topic of focus is going to be on angles in standard form. And what does that mean when we talk about angles in standard form? So we know that angles are formed when you have two rays that intersect at a point called the vertex. But angles in standard form mean they're angles that are formed in a certain position in the coordinate plane. So an angle in the coordinate plane is in standard form when the vertex is on the origin. So again, the vertex is on the origin, okay? In other words, at point 0, 0. And one ray lies on the positive x-axis. So as you can see here in the example, you can see that we started off with a ray on the x-axis pointing in the positive direction. And the vertex is actually at the origin right there at 0, 0. The ray on the x-axis is called the initial side. So that initial side, see, I'll draw a little arrow, is right here. That's the initial side we just created. Now the terminal side is the side that gets rotated. So that's the other side here. In this case, this one was rotated theta degrees. We don't know exactly what theta is here. It's obviously somewhere between 90 and 180, but it is rotated in the counterclockwise direction. Oops, I'm having trouble drawing that, just a second. Okay, but again, that side is called the terminal side. Okay. Now, when we go in the counterclockwise direction, which you can see this angle is being rotated in that direction this time, angles are given positive measures, angle measures. So this angle would be maybe approximately, I don't know, positive 135 degrees, something like that. That's between 180 and 90 degrees. Now, if instead we were going clockwise direction, in other words, going down first, so if we had started on the x-axis and we went down like this instead, clockwise, that's a negative angle, and I think probably for obvious reasons, because from the x-axis you have to go down if you're going clockwise. So that's why they're negative measures. So if you see a negative angle, that means you're going to start from the x-axis and go down or go in the clockwise direction. Now, one full revolution or one full time around the coordinate plane would result in 360 degrees. So the first thing we're going to look at is how we can sketch an angle with a given measure in the standard position. Now, notice it says sketch. We are not going to get protractors out and be super precise on these. We're just going to sort of, I guess in a way, eyeball them, but try to be as accurate as we possibly can. So in this first one, they want me to sketch a 75-degree angle. And so again, I always start off on a positive x-axis with my initial side. This is a positive 75 degrees, which means I'm going to rotate in the positive direction or rotate up 75 degrees. And since right straight up is going to be 90 degrees, then I know it must be just shy of that. So maybe approximately here would be a 75-degree angle in the positive direction. So the next one is negative 160. So again, we always start off in the same position on the x-axis, but this time the negative tells me to go down first. So I'm going to rotate down, and because when I go through each quadrant that's going an equivalent of 90 degrees, I know I'll go 90 degrees, but then I have to go almost all the way to 180 degrees, just shy by about 20 degrees, or by 20 degrees. So it's actually going to come all the way around here into this quadrant, and it's going to end up maybe a little further than that. Maybe I should redraw that a little closer if I want to be more accurate. Maybe it's only going to be 20 degrees away from the x-axis on the other side, so maybe right there would be negative 160 degrees. Now, it would have been easier for me to talk about this if I could refer to quadrants in the coordinate plane. So let's go back and real quick review the different quadrants. So there's 4, and that's what quad means, right? So the first quadrant is right here. So this is quadrant number 1. This is quadrant number 2. Sometimes they'll write it like this in Roman numerals. This is quadrant number 3. Again, they sometimes write it in Roman numerals, though they'll say this is 3. And this is Roman numeral 4, quadrant 4. Now Roman numeral 1 and 1 are basically the same thing. It's just written like this instead. So this terminal side ended up in quadrant 3 because I went negative 160 degrees. Whereas in the first angle, it ended up in quadrant 1. So this next angle is quite a big angle. It's 430 degrees, which means I'm going to have to rotate more than one time around this circle. So again, I always start off on the x-axis. This one says to go a positive 430 degrees. So that means I'm going to go all the way around. There's 90, there's 180, that's another 90, which is 270. There's 360 degrees. So I've already gone 360. And that means I need to go 70 degrees more, because if I take 360 and subtract that from 430, that leaves me with 70 degrees more to go. So that means I'm going to go another 70 degrees, maybe right about here, and that angle would be right about there. So I end up back in the first quadrant because I went all the way around plus another 70 degrees. Now when you draw these angles, you don't have to put these little arcs, but I really feel like they're helpful because then you can see that I went all the way around plus an extra, and even if you want to put an extra 70 degrees in there, then that just kind of helps you to see that you've gone more than one time around. Okay, so I think we have that down. Again, if you're kind of confused about like terminology, you can always go back and look here at the top of where we've defined all the terms, or if you forget which one's positive and which one is negative, here again, just take a look here at the top under our notes. So next we're going to take a look at a new unit of measure that relates to a circle. It's called a radian. Now we've talked a little bit about radians before because when we had to change our calculator to degrees, we had to change it from radians. So what is actually a radian? Well, what a radian is it's a unit of angle measure based on arc length. Maybe remember arc length from geometry. Arc length means that we're trying to find the length of part of the outside of a circle. So like in this case, let's say we wanted to know like the length of this arc of the circle. Oops, right here. Sorry, my stylus is acting up again. So on this circle over here, that's an arc length right there. That's a length of part of the circumference of the circle. And that would be a way, like a linear way to measure that, that turn from, say, this point here to this point here. Whereas an angle, we'd measure it in degrees. We'd say to turn from here to here, we'd have to rotate through so many degrees. So this is really more of like I'm traveling on the outside of this circle and I'm actually, like, say, walking around this part. How far do I walk? So it's a linear measurement. A radian is a linear measurement. Now, 1 radian is defined as the measure of the angle formed when the radius is equivalent to the length of the intercepted arc. Recall that the circumference of a circle is 2r pi. Therefore, 360 degrees is actually equal to 2 pi. Or in this case, 2 pi r. But when we talk about a unit circle, we say that the radius is 1 radian. So that r here in this formula turns into 1, so that just leaves us with 2 pi. So to go along the outside of this circle that has a radius of 1, we would have to go 2 times 1 times pi, or 2 pi radians. So remember circumference, we find circumference by using the formula 2 pi r. So that's really all we're doing here is it's like we're giving a measurement of the whole circumference of a circle with 1 as the radius. Now if I only went 180 degrees instead, so instead I didn't go all the way around, I only went, say, halfway around 180 degrees, that would be equivalent to just pi radians. So we use this fact that 360 degrees is equal to 2 pi, or that 180 degrees is equal to pi radians, if we want to convert from degrees to radians. And you know that anytime you have two things that are equal, you can make a conversion factor out of it. You could either use the 360 and the 2 pi, or the reduced version would be 180, and pi. You could either write pi radians over 180 degrees, and those would be considered just a fraction that equals 1 because they're equal to each other. And that's how we convert, like when we say convert 1 foot over 12 inches or 12 inches over 1 foot. We can convert because those are equivalent measures to each other. Or we could also flip that ratio and compare 180 degrees to pi radians. And we just have to use whichever conversion factor has what we're looking to convert to in the numerator position of the conversion factor. So, for instance, let's say we had 30 degrees, and we wanted to know what the radian equivalent for that was in what's called the unit circle, or this circle. So all we'd have to do to convert is we would pick the one that has what we want, which is radians, on the top. So in this case, that would be the pi radians over 180 degrees. And so the degrees part will cancel, so these little degree symbols will cancel there. And what's remaining is 30 times pi over 180, or 30 over 1. So all we have to do now is just multiply and reduce. So I know that 30 actually goes into 180, so I could cancel out that 30, make it 1. I could cancel out the 180 and make it 6, since 30 goes in to 186 times. And that would leave me with pi over 6, or 1/6 pi radians. So going 30 degrees is equivalent to going pi over 6 radians. Now think about what that means. So 30 degrees on the circle over here would be like, say maybe right here. Oops, let's see. Maybe right there, that's about 30 degrees. And that's 1/6 of the way from going all the way to pi, which is all the way over here. So that is 1/6 of the way to 180 degrees is what that's saying. So now I'm going to convert 150 degrees using the same conversion factor, pi over 180 degrees, or pi radians, I should say. We usually abbreviate that as like rads. So this time I can cancel out, let's see, 30 out of 150 5 times, and 30 out of 180 6 times, which leaves me with 5/6 pi, or 5 pi over 6. And that's how we usually write it, is we'll write it all as one single fraction, 5 pi over 6. And again, that's radians now. So we're going to designate number 6 as a U-tri. Notice that the degree measure is negative, which will mean that our radians will be negative. So keep that in mind. Pause the video now and convert 220 degrees, negative 220 degrees, into radians. Pause the video now. So thanks for giving that one a try. That turned out to be negative 11 pi over 9. Both negative 220 and 180 were both divisible by 20, so I was able to reduce that fraction down to 11/9. Okay, so now what about if we are given a measurement in radians, but we want to convert it to degrees? And this is the one that typically we do more often because we are so much more comfortable dealing with degrees. So if we see radians, we usually want to switch it over real quick to degrees. And this is how we do that. We just take that conversion factor and we just flip it and use it in the reverse. So we'll use, since we want degrees, we're going to put 180 degrees on the top, and we'll put that pi radians on the bottom. A lot of times they'll just leave rad off when they give a radian measurement, like 4 pi over 3 or 4/3 pi. So it really is there, radians is there, but usually when you see pi, you just kind of assume it's radians. Sometimes they'll just leave it off. But so the radians, if they were listed, would cancel out. But the other thing that I can tell is going to cancel out right away is the pi. So this actually makes this conversion very easy, because now I just have to multiply 4/3 times 180. So 4/3 times 180 is 240, and that's in degrees, so 240 degrees. So just taking that conversion factor and flipping it allows me to use it then to convert to degrees. So negative 5 pi over 36. Let's convert that into degrees. So 180 degrees. This means it's going to be a clockwise rotation, right? Because, again, it's negative, so it's going in that negative direction. So I see that the pi's are going to cancel out. And then I have negative 536 times 180. So 536 times 180 degrees is 25 degrees. So this is equivalent to going negative 25 degrees. We're going to go ahead and designate number 9 as a U try. So go ahead and pause the video now and give number 9 a try, converting to degrees. Pause the video now. All right, thanks for giving that one a try. 7 pi over 4, or 7/4 pi, is equivalent to 315 degrees. Okay, let's turn the page. So in this lesson, we are learning lots of new terminology, and the next up is the term coterminal angles. So what does it mean for an angle to be coterminal? So a coterminal angle basically means just an angle with a different measure that ends up in the exact same position. So angles in standard position with the same terminal side are called coterminal. And they're asking us in these examples to give 2 coterminal angles for each given angle, one positive and one negative. And so the easiest way to do that when it's in degrees is simply add or subtract multiples of 360. And the reason why that works is because 360 degrees is the whole way around the circle. So if you went positive 360 degrees, it would take you in the counterclockwise direction right back to where you started. And if you went negative 360 degrees, it would take you clockwise right back to where you started. And so that's really just a simple task to give coterminal angles. It's just a matter of adding multiples of 360 or 360 itself to get, and there really is infinitely many possibilities here. So like I could add 720, I could subtract 720, I could add 1080 or subtract 1080. Those are all multiples of 360 degrees. But the most common ones that are given are the ones that are closest to the angle. So usually you're just, if you can do it by adding 360 or subtracting 360, those are the ones that are usually the most commonly given ones. So for 65 degrees in the coordinate plane, you'd end up in the exact same spot if you instead went 425 degrees. Or if you went the other way around and went negative 295 degrees, you'd end up at the exact same spot. So again, for the 425, I took 65 and I added 360. And then I took 65 and I subtracted 360 to get the 295. Now on the next one, 540 degrees, if I added 360 degrees, I would get 900. So 900 is a coterminal angle to 540, but I could have also gotten a positive coterminal angle by actually subtracting from 540 because it's so big already. 180 could also be one of the positive ones. So those are both 2 possible positive ones. And then a negative one, I couldn't just simply subtract 360 one time because that gave me 180. I'd have to subtract it twice or subtract 720 degrees, and that would actually give me negative 180 degrees. So that would be the first negative coterminal angle would be, I'd have to go negative 720 degrees around the circle. That's twice around in the negative direction to get me back to that same exact spot. So that's a really pretty simple task when you have degrees. It's just a matter of adding or subtracting multiples of 360 degrees. So what about if instead they give you radians? Well, there's really two options here. When they give you radians and they want it, you would assume that they want it then in radians in terms of the coterminal angles. So one thing you could do is convert 13 pi over 18 into degrees and then find the degree versions of the coterminal angles and then convert back to radians. Or you could just simply know that instead of 360 degrees, one whole way around the circle is 2 pi. So instead you could just simply add or subtract 2 pi or multiples of 2 pi. So you could either add 2 pi or subtract 2 pi. And that way we would just stay in radians the whole time. So let's say I did that, and let's say I first wanted to add 2 pi to 13 pi over 18. Well, the first thing I notice is these don't have a common denominator, so I would have to get a common denominator to add them. So 13/18 pi has a denominator of 18. So if I wanted to make 2 pi have a denominator of 18, I'd have to multiply the top and the bottom by 18, which would make that 36 pi over 18. Now I have a common denominator, and I could just simply add those to get my positive coterminal angle. But I could also do the same thing, but instead subtract 36 pi over 18, and that would give me my negative coterminal angle. So add them together. I'm going to add the numerators. That makes, let's see, 49 pi over 18, so that's my positive coterminal angle. And then my negative coterminal angle, 13 minus 36, is 23, negative 23, so negative 23 pi over 18 is going to be my negative coterminal angle. And again, that way I'm in radians, which is how the angle was given to me to begin with. So instead of doing 360 when you have radians, you're going to do 2 pi instead. And of course you'll have to get a common denominator in order to subtract or add fractions. Let's try one more together. Actually, you know what? Let's make this one a you try question. If you get stuck on adding or subtracting the fractions, you can always tune back in and when you're done, give it a try and we'll go over it. But let's designate 13 as a you try question and find a positive and a negative coterminal angle to 14 pi over 9. Go ahead and pause the video now. Okay, thanks for giving those a try. So when I added 2 pi, I had to get a common denominator for 2 pi, and so when I wrote that with a denominator that is the same as the 14 pi over 9, I got 18 pi over 9 right here. And so then I added that and I subtracted that from 14 pi over 9, leaving me with 32 pi over 9 and negative 4 pi over 9. So again, when you're working with angles to begin with, you want to add or subtract multiples of 360, and instead you would want to add or subtract multiples of 2 pi. So for instance, like 2 pi or 4 pi or 6 pi, because if you try to do like say 3 pi, that's only going 1.5 times around the circle, not 2 times. Going 2 pi is one time around. So just stick with what you have. If you have radians, stick with radians and just add and subtract 2 pi instead. Now this next skill we're going to look at is really going to become very important as we move into this thing called the unit circle. And it's called finding a reference angle. So the first thing you need to know about a reference angle is this. Well, so let's look at the definition. So for an angle theta in standard form, the reference angle is the positive acute angle formed by the terminal side and the x-axis. So those are the things that I wanted to point out that are super important, that they're positive, it's acute, meaning less than 90 degrees. I guess it could also be 90 degrees in some instances, and also formed with the x-axis. So one of the sides is the x-axis, okay? So that's how we're going to establish the angle that we're actually looking for is the one that's formed with the x-axis, okay? So maybe I should phrase it like that, formed with the x-axis. So when you're trying to find a reference angle, I think the best process is to actually sketch that graph. So if they don't give you a coordinate plane, just sketch your own little coordinate plane like we have here and sketch the angle. So you can figure out which quadrant you're in to begin with. So 225 degrees. Well, so we're going to look at some key points in this coordinate plane in parameters. So when we start off on the x-axis, we're at 0 degrees. Then at the top, it's 90 degrees, then 180 degrees, then go another 90 degrees, that makes 270 degrees, and then back to the x-axis makes 360 degrees. So when I want to graph this 225 degree angle, remember I'm going to start on the x-axis. It's positive, so that means I'm going to go around in the counterclockwise direction. And I know that if I go around to the x-axis on the opposite side, I've gone 180 degrees, but I want to go 225, which means I need to go 45 degrees more, and that's going to put me, so I went 45 degrees further, that's going to put me right here in this spot in the third quadrant, excuse me. And what I really want to know is the angle that's formed with the x-axis, and I want the acute angle that's formed. So you can see there's two angles formed with the x-axis. There's this one over here, but that one's not acute, and then there's this one here, and that angle right there represents the reference angle, and that's the one we want. So the reference angle for 225 degrees would be 45 degrees, because that's how many degrees I had to go past the x-axis at 180 degrees to get to this angle. So that reference angle is the angle that's formed with the x-axis, and this one meets the criteria. It's positive, it's acute, and it's formed with the x-axis. Now the thing you need to know with reference angles is it doesn't matter which direction you're going to get back to the x-axis. Reference angles are never considered to be negative, so you don't have to worry about like which direction you're going to get to the x-axis and making it negative or whatever. They're always going to be considered positive. So negative 310 degrees. Well, again, so we're going to start on the x-axis, and I know I'm going to rotate around, so there's 90 degrees that way. There's 180 degrees. There I've gone 270 degrees. And if I have to go another, I have to go now to negative 310 degrees, and I've already gone negative 270. That means I have to go 40 more degrees past this. But what I actually need to know, so that's taking me negative 310 degrees. So let me write that here, negative 310. But what I want to know is the angle that's over here that's formed with the x-axis. So that closest route back to the x-axis is that angle right there. And that is negative 310 degrees is actually 50 degrees away. Like that right there is a 50 degree angle. It's 50 degrees from the x-axis. So I know my reference angle is 50 degrees. Okay. Now you'll start to kind of get a feel for this, and you might figure out like little formulas, I guess, if you will, that you can use. But those formulas that you think of never really work when the angle is negative. See, like for instance, with number 14. I could have used this formula 225 degrees minus 180. So you're either going to add or subtract, subtract 180 from the angle, or take the angle and subtract 180, or possibly take the angle and subtract it from 360. But it depends on the quadrant that you're in, and so there's all these different formulas, and they only work for positive angles. So in my opinion, I think it's best to just graph the angle, to sketch it, and then just see how far away from the x-axis you are. That's a surefire way that works every single time. Now finally, we want to find the reference angle for 2 pi over 3. Now, here again, I could just work in degrees, and I could then know that, I'm at 0 here, and then going up to 90 degrees would be, I'm only halfway to pi, because you know how pi is over here at 180 degrees, so this would be 1/2 pi, or pi over 2, and then down here would be 3/2 pi, or 1/2 pi, that's 3 pi over 2, and then back around all the way would be 2 pi. So you could kind of think about it in radians, or you could convert this to degrees and work in degrees to find the reference angle. But then once you get the reference angle, you have to convert it back to radians. So it's almost, if you can, try to work within the measurement that they gave you, which is radians. So I know that to go 2/3 of the way to pi, I would actually have to start on the x-axis, and 2/3 of the way to pi would be approximately here. And if I go 2/3 of the way, then that means let's see, let me color that in just to show you. So then that means what's left, if I already went 2/3, is 1/3, right? So that means the reference angle is 1/3 pi, or pi over 3. So if instead I had done that in degrees, I could have switched 2/3 pi into degrees, which is 120 degrees. I could have done that. And then, oops, I could have said this is 120. And then found out that then the reference angle would be 60 degrees, because I'd have 60 degrees more to get to 180. And then I could take the 60 degrees and I could then convert it back into radians. So that's just a lot of converting. And in cases like this, where it's pretty obvious, 2/3 and 1/3 makes the whole pi, then it's kind of easiest just to stay in radians. But that is still an option. If you feel more comfortable and you want to convert to degrees, then once you get your reference angle, convert back. You'll still get the effect and get the final answer. So in this final part of the lesson, we're going to take a look at calculating trig ratios for a point that is located on the terminal side of one of these angles in standard form. And we're going to create a right triangle with a point on the terminal side and the x-axis. So where that angle, theta, is like the reference angle that we just learned how to find. So first of all, let theta be an angle in standard position, or standard form, and P, with coordinates x, y, be a point on the terminal side of theta. So looking over in this drawing, we've got a sample of that here. We've got a terminal side that ended up in the second quadrant, and a point that's on it. So that coordinate, that point xy, would have to have some sort of negative x value and positive y value, because to get to that point you have to go left and up. And so by connecting back to that x-axis, we create a little right triangle, which now we can calculate trig ratios for the reference angle to theta, which is actually made with the x-axis, the closest route, and that's this angle right here. So this turns out to be theta right there. And we can, if we were able to find the length of the hypotenuse, which we could easily do using Pythagorean's theorem, so a squared plus b squared equals c squared, we could use to find what they have labeled as r here, which is that hypotenuse. And the x and the y actually represent the two legs of the right triangle. So like, for instance, something like this point right here might be at, say, -4 and 3. So that x coordinate, or this side of the right triangle, the adjacent leg, would be -4, and the opposite would be +3. So that -4 kind of looks funny on a triangle to say a side is negative, but really that negative is just indicating the direction that you have to go to create that side. You have to go to the left. So we could still use those two numbers to find that hypotenuse using Pythagorean's theorem, because remember, when you square anything, even negatives, it turns out to be positive anyway. So then we could use Pythagorean's theorem, calculate the missing hypotenuse, and then find out the trig ratios. So here, at first we're going to just look at this in general, and taking a look at this triangle, if I wanted to calculate the sine of theta would actually be the opposite leg, which happens to be y, that's the y coordinate, over r. The cosine would be x over r. The tangent would be y over x. And then the reciprocal ratios, cosecant would be r over y. The secant would be r over x. And the cotangent would be x over y. So for instance, if we had those coordinates I talked about where that point was at negative 4, 3, and we had calculated the tangent of theta would be the opposite, which is 3, over the adjacent, which is negative 4. So the tangent of theta would be negative 3/4. Now if we wanted to find the other trig ratios, we'd have to find out what that hypotenuse is by using Pythagorean's theorem. So let's take a look at creating one of these triangles by plotting the point 5, negative 2 on the terminal side of theta in standard form. So if I wanted to plot the point 5, negative 2, that means I'd have to go 5 units to the right, and then I'd have to go 2 units down, which would put me in this fourth quadrant. And then connecting that point to the origin, and then because that triangle started on the x-axis, or that angle, I guess I should say, but we always create that triangle going back to the x-axis. So this is what that would look like. And theta would be the reference angle, which is the angle that's formed with the x-axis, so that would be right there. The two sides that we know would be those coordinates, 5 and negative 2. And then we could use those two sides to find the hypotenuse. So 5 squared plus negative 2 squared is equal to r squared. And 5 squared is 25. Negative 2 squared is 4. Add those two together, we get 29. And 29 is equal to the radius squared, so we'd have to take the square root. So that would make our hypotenuse be the square root of 29 for this triangle. And now we could then calculate all these trig ratios using those three sides. So the sine of theta, because the side across from theta is negative 2, would be negative 2 over the square root of 29. And before we rationalize it, we could flip it to get the cosecant, and that would make it negative square root of 29 over 2. Doesn't really matter where the negatives is, so I usually put it with the numerator. And if we rationalize, then the sine would become the negative square root of, or 2 times the square root of 29, over 29. Now the cosine would be 5 over the square root of 29. And we'll rationalize it in a minute, but I'm going to flip it first to get the secant, which would be the square root of 29 over 5. And then rationalizing the cosine would give me 5, oops, that doesn't look like a 5, 5 square root of 29 over 29. And then finally the tangent would be the opposite, which is negative 2, over the adjacent, which is 5. And the cotangent would be the reciprocal of that, or negative 5 over 2. And again, the 2 really is the one that has the negative on it, but it doesn't matter where you put a negative. So typically you either put it out in front of the fraction or you put it with the numerator. So those would be the 6 trig ratios for a point on a terminal side in the coordinate plane. So that does it for today's lesson. Thanks for coming to class.